All right, let's talk about a technology that sounds like it's straight out of science fiction. It promises to change, well, pretty much everything, from creating new medicines to completely breaking the internet as we know it. And it does this by tapping into the strangest, most bizarre rules of physics. So let's dive right into the wild world of quantum computing. I mean, it's a totally fair question, right? Why on earth are we trying to build a computer based on the weirdest laws in the entire universe? It's ridiculously hard to do. So there has to be a really, really good reason we're even bothering. And, well, there is. The truth is, we're starting to run into problems, huge, important problems, that our current computers, no matter how powerful they get, will just never be able to solve. Think about it. The computers in our pockets, in massive data centers, they're incredible. But for all that power, they're hitting a wall, a fundamental limit. Yeah, they're great at a lot of things, but when it comes to certain game-changing problems, I'm talking about things like designing brand new drugs molecule by molecule or cracking the codes that protect our entire digital world, they just fall flat. We're not talking slow. We're talking it would take longer than the age of the universe slow. We've basically hit a computational brick wall. Okay, and this right here, this is the core of it. This is why it's a whole new ballgame. On one side, you've got your regular computer. If it has a bunch of bits, say n of them, it can only be in one state at any given moment. But a quantum computer, with n qubits, it can explore all 2 to the power of n states, all at the same time. Now, that might sound a little abstract, but this isn't just a small upgrade. It's an absolutely massive, exponential leap. The analogy is perfect. It's like trying to find the right key for a lock. A classical computer tries one key, then the next, then the next. A quantum computer basically gets to try every single key in the world, all at once. So how is that even possible? What's the secret sauce here? Well, it all boils down to one fundamental, revolutionary building block, the quantum bit. You've probably heard of it. It's called the qubit. But before we get to the qubit, let's give a quick shout out to the hero of the last, 70+ years, the good old classical bit. It's just beautifully simple, isn't it? It's a light switch. It's either on or it's off, a 1 or a 0. Our entire digital reality is built on that simple, rock-solid idea. A qubit, though, it plays by a whole different set of rules, the quantum rules. So forget the simple on-off light switch. I want you to picture a dimmer switch. A qubit can be all the way off. That's a 0. It can be all the way on. That's a 1. Or, and this is where it gets weird, it can be somewhere in between, a blend of both 0 and 1 at the exact same time. This absolutely mind-bending property is called superposition, and it's the first superpower that makes a quantum computer possible. So qubits basically have 2 superpowers. The first, as we just saw, is superposition. That's what lets them check out a whole bunch of possibilities at once. But the second one, this one is even weirder. It's called entanglement. You might have heard of it as what Einstein called spooky action at a distance, and it is spooky. This is where you can link 2 qubits together and they become connected on some deep, fundamental level. What you do to one instantly affects the other, even if they're on opposite sides of the galaxy. It's this bizarre, powerful connection that really unlocks the computational power. Okay, so we have these amazing quantum properties, superposition and entanglement. But, and this is a huge but, actually using them isn't as simple as writing some clever new software. No way. Building a machine that can control this stuff, it is, without a doubt, one of the hardest engineering challenges we have ever faced. We're literally trying to build machines that can manipulate the fabric of reality at this single atom level. It's just staggering. And what's crazy is there isn't even one single way to do it. It's like a race with a bunch of different teams, each betting on a different technology. You've got teams like Google and IBM using these little superconducting circuits. They're super fast, but they're also super fragile. Then you have other groups who are literally trapping single atoms, ions, in magnetic fields. And some are even trying to build qubits out of particles of light, photons. Every single one of these approaches comes with its own mountain of challenges, and right now, the race is on to see which one, if any, can actually be built at a large scale. And when I say monumental challenges, I mean it. Just to give you a sense of how extreme this is, many of these quantum computers have to be kept colder than the coldest vacuum of outer space. We're talking temperatures just a tiny fraction of a degree above absolute 0, the theoretical point where all atomic motion stops. And why? Because the quantum world is just unbelievably delicate. The slightest bit of heat, the tiniest vibration from the outside world, is enough to completely shatter that fragile quantum state and ruin everything. All right, so let's say we do it. We build these insane, super cold, incredibly complex machines that can control these quantum states. What now? What do we actually do with them? And this is a key point. You can't just install your favorite app or operating system on a quantum computer. It doesn't work that way. You need a completely new way of thinking, a new set of rules. You need brand new algorithms designed specifically for this quantum world. And this is where the theory suddenly gets very, very real. You have things like Shor's algorithm, that's the big one that could, in theory, crack most of the encryption we use today to protect everything online. Then there's Grover's algorithm, which is like a super-powered search engine for finding a needle in an impossibly huge haystack. And right now, a lot of work is going into these hybrid approaches, where we link up our best classical computers with these early quantum devices to try and get the best of both worlds. Okay, I've mentioned a few times now that this whole quantum world is fragile, right? Well, that fragility, that core problem, it has a name, and it is, without question, the number one villain, the biggest obstacle standing in the way of a real quantum revolution. And the name of our villain is decoherence. Here's the best way to think about it. Imagine a qubit in its perfect quantum state is like a single, beautiful, perfectly tuned guitar string vibrating. Decoherence is what happens when anything from the outside world, a tiny bit of heat, a stray magnetic field, even a random vibration, touches that string. The beautiful pure note instantly dissolves into just random noise. The quantum magic is gone, and your calculation is completely ruined. This whole problem is why I'll hear experts say we're living in the NISQ era. And NISQ stands for Noisy Intermediate Scale Quantum. Let's break that down. Intermediate scale means we can build machines with a respectable number of qubits now, but noisy is the key part. It means they're constantly being bombarded by decoherence and all sorts of other errors. And that noise seriously limits how big and how complex of a problem we can actually run on them right now. So how do we fix it? What's the plan to fight all this noise? Well, the main strategy is something called quantum error correction, but the scale of this challenge is just mind-boggling. The basic idea is that to create one single, perfect, stable, logical qubit that's protected from noise, you might need to use thousands of our current, noisy, physical qubits to back it up. The overhead is just astronomical. But right now, most people agree it's the only way forward to get to truly powerful, fault-tolerant machines. So we've got these incredible challenges, this noise problem, this massive engineering lift. Yet the race is still on. Companies and countries are pouring billions into this. So why? Why go through all this trouble? Because if we can pull it off, the payoff isn't just big. It's potentially transformative for all of humanity. Just imagine it, a fully working, error-corrected quantum computer. It could let us simulate molecules with perfect precision. That means designing life-saving drugs or creating revolutionary new materials from the ground up. It could help us discover new catalysts to fight climate change. It could solve optimization problems so complex they're basically impossible today, completely revolutionizing things like logistics, finance, and even artificial intelligence. It would be like having a microscope to see the fundamental workings of nature itself. So that's where we are. We're left with this huge question. The science behind it all is absolutely beautiful, and the engineering effort is nothing short of heroic. But the mountain we still have to climb, man, it is steep. So what do you think? The next few decades will be the real test. Will we finally conquer the noise, tame the complexity, and unlock this incredible revolution? Or will the true power of the quantum world stay just tantalizingly out of our reach?